Okay, so this is section 5.8, inverse trigonometric functions, and we're going to integrate these things. The three formulas that you need to know from this section are here. Of course, the one that's going to get, the two that are going to get most of our work done are these two, the arctangent and the arcsine. The one difference is that the arcsine doesn't have the 1 over a term that the arctangent does. So our first problem that we already did was problem number 4. And it's just a matter of manipulating things so that it eventually looks like your arctangent formula. We did that by noting that that was a 3x quantity squared, and then with a quick little u substitution. In a similar way, down here, problem number 14, a little u substitution gets us on the right path here. So with our u substitution, if u equals cosine of x, du is minus sine of x dx. My bias in doing my u substitutions is this. I like to solve for what's in the integrand. So in this particular case, I've got a sine of x dx. So that means for me, I'll move this negative sign to the other side and get minus du is the same thing as sine of x dx. I like that. That way I can make a nice direct substitution. Let's see what that gives us. I get a minus du over 7 plus u squared. And that's looking pretty good. Of course, you can take the minus out in front because it's a constant. So comparing that to our formulas, this one looks mostly like the inverse tangent. So let's see if we can integrate it like that. We've already got a u squared here, so that's looking pretty good. The only thing we don't know exactly is what is a. But a squared is 7. That's what this is. It's the square of our term a. So what does a have to equal? Square root of 7. So a is the square root of 7. And that's pretty much all we needed. So it's going to be 1 over a, which is 1 over the square root of 7, times the inverse tangent of u over a. So it's going to be u over square root of 7 plus your constant. You could write inverse tangent or arctan. You could rationalize this or not. This is not an algebra class, so I'm not going to worry about it if you don't rationalize it. Here it is rationalized in case you're curious. Arctan of, where is it? Cosine of x over the square root of 7 plus your constant. Yay! Oh yeah, we have a negative in here someplace too. Yeah, so the negative, thank you. So that negative here, just put it out in front there. Now, the nice thing about calculus is that we can kind of abuse our constants. The negative does apply to a constant, but it's still a constant. So we're just going to leave it as a plus c. We don't have to put a minus c. Thank you. All right, how are we looking on 14? Okay there? Let's keep going. I'm going to keep showing you more tricks for your integration. And the next problem I think I want to try is problem number 34. And you know, we're going to use this trick a couple times. So let me do a quick little bit of review here for you. Suppose you had y plus 3 squared, a binomial squared. I sincerely hope that at this level, no one says, oh, that's y squared plus 9, right? You can't do that. You can't distribute that squared term. Instead, what you have to do is do y plus 3 times y plus 3, y squared plus 3y plus 3y plus 9. This is what's called a perfect square trinomial. A lot of times it's convenient if you have a perfect square trinomial. So you're going to want to make that kind of thing happen. So if I was reversing this process, if I had y squared plus 6y plus something, then what I need to do is a process called completing the square. So somehow or another, I need to be able to look at this and realize that, you know what, I need a 9 here. How am I going to look at this and come up with 9? What's the trick that I need to do here? Yeah, so you take half of this and then square it. So half of 6 is 3. 3 squared is 9. That goes here. And then this factors as y plus 3 squared. So that's your process of completing the square. We're going to use that a couple times in this section, so it doesn't hurt to refresh your memory on how that goes. Well, let's not waste any time in using that one. Let's start with problem number 34. I'm just going to do a sound check here real quick because I bumped the cord. Recording devices. Yep, we're all good. So problem 34 is the integral of dx over x squared plus 4x plus 13. It's a definite integral from -2 to 2. We'll worry about that at the end. For now, though, we got to whip this into shape into something that we can integrate. And the trick is going to take advantage of the completing the square stuff that we just dealt with. So, again, this is going to be the integral from -2 to 2. Let me give myself a little bit more room. Now, if I was to complete the square and said, all right, let's just write a perfect square trinomial here, what number is going to go right here? 4, right? Half of 4 is 2. 2 squared is 4. So I'll put a 4 here. Now if I put a 4 here, what's the rest of it? What's left over? Well, we're not adding it in and taking it out. We're just splitting this up. So I've got 4 here, and that leaves 9 here. So 9 there. Now I can rewrite this as -2 to 2 of dx. Now this part here is a perfect square. So let me rewrite that here. What do I square to get that? X plus 2. And of course here, I've got a 9. That's looking pretty good. We can make ourselves a little u substitution and finish this one off. All right, but do you see the big trick that I want you to get is this part right here, is completing the square so that I transform this into something that looks like an inverse tangent. Now, as far as myself, I'm going to make a u substitution to finish this one off. And at the same time, I'm going to change my limits of integration, because my new limits of integration have to reflect my new variable, which is going to be u. By the way, what should I let u equal? X plus 2. The nice thing here is that du equals dx. That's great. If you see du equals dx at some point when you're doing some integration, that means you can kind of almost think your way through the antiderivative. It means that you're not going to get a lot of constants coming in or out because du equals dx. But the one thing else that I'm going to do here is this. I'm going to change the limits of integration. So I'm going to regard this as a function. If I put in -2 for x, or 2 for x, what should I get for u? Negative 2 plus 2 is 0. 2 plus 2 is 4. So my new limits of integration are 0 to 4. 0 to 4 du 9 plus u squared. Looking good. Now what? There's your arctan pretty much right there, right? So what does a equal for us this time? 3. So I get 1 over a, which is 1 over 3, tangent inverse of u over 3. Do I need a constant? No, because I've got a definite integral. The constant would subtract itself off. So we're good there. Let's plug in some limits. There's going to be 1/3 tangent inverse of 4/3 minus 1/3 tangent inverse of 0. And we are going to get a little bit of simplification here because the inverse tangent of 0 is 0. So that just disappears altogether. You're just left with 1/3 tangent inverse of 4/3. Now that's a nice exact answer. We will go through doing some of these things on a graphing calculator and coming up with numerical answers, but if I ask you for an exact answer, this is what I want. I want a nice expression. I don't want decimals. How's that one look? We're okay on 34? I'm relying on you. If you have something that just doesn't look right, please ask. It helps you out, helps me out. Yes, please. Good question. Because these limits apply to the variable x. And when I change the variable to u, I have to change the limits of integration because I got a new variable that I'm working with. So I just did that. The alternative to this, to changing your limits of integration, would be right here. When you found your antiderivative, you would write limits of a and b here because we don't know what those limits are. And then right here, you would just go back and say, okay, well, this is really x plus 2. And then you could go back and use your old limits. So equivalently, I could say, all right, that's 1/3 tangent inverse of x plus 2 over 3 from negative 2 to 2. So the old limits. But guess what? If you plug in these limits at 2 and negative 2, you're going to get exactly what this is here. So it's either way will work. It's whatever you're comfortable with. I like changing my limits and not looking back. But if you're more comfortable saying, you know what, I just like the old limits, I'm going to go back and finish this problem in x, then that's fine too. You don't have to do it my way. Okay? All right, appreciate the question. Anything else on 34? Okay. Let's see. Let's try problem number 36. Somewhat similar to the last one. And again, these are tricks that, boy, unless you see them, they're hard to come up with on your own. You're not going to necessarily look at all these and go, oh, hey, I got it. I know what to do. So, I mean, if you can, I'm surprised you're in this course. 2x minus 5 over x squared plus 2x plus 2 dx. Now, one thing that could catch your eye, and don't overlook the power of a u substitution. One thing that could catch your eye is this. The derivative of x squared is 2x. So, but we can't just take, part of this denominator. Let's think about what would happen if we took the whole denominator. U equals x squared plus 2x plus 2. What would be my du term if I did that? Yeah, 2x plus 2. Well, it's a linear term. So's this. Here I've got a 2x minus 5. Here I got a 2x plus 2. So is there a way that I can monkey around with the numerator? I want a 2x plus 2. Now, Kevin, here's where what you were saying earlier is a little bit closer. If this is 2x plus 2, what else would I need here to make this equal? There you go, minus 7. All right, so these two things are essentially the same now. The only difference is I split up that negative 5. So a nice little trick, and let's try and understand why I did it. This part right here, boy, those two together are going to lend themselves to a simple u substitution. So 2x plus 2 over x squared plus 2x plus 2 minus the integral of 7 over x squared plus 2x plus 2, and I should have a dx on both of these. This one we're in good shape. This is just a u substitution. If you let u equal x squared plus 2x plus 2, du is 2x plus 2. Yay, that's good. That one's going to work out pretty nice. We'll get the integral of d, actually should have put a dx here. This whole term here is exactly what I have up here. So here and here, those two things are the same. So that's my du term. What's the denominator? Just u. Yay. So let's see how good you are on your Calc 1 stuff. What's this integral? What's this integrate to? Well done. That one's a natural log of the absolute value of u. Now we're not going to worry about the constant yet. We'll put that in at the very end when we finish dealing with this one. Yeah, like I said, we're not going to worry about the constant yet until the very end. Yeah. Now, over here, any ideas what we're going to do with this one to integrate that one? How so? All right, we can take the 7 out in front, but it's dealing with the denominator that's going to be a little bit challenging on this one. So, any ideas? What's that? Complete the square. It's going to be just like this one right here. So, we'll take the 7 out in front. Dx, x squared plus 2x plus something plus something. So take a second for yourself and decide what value, what number here completes the square. Well, half of 2 is 1. 1 squared is still 1. So 1 here. Now keep in mind that we're splitting up that 2. So if 1's here, 1's outside. All right, so let's keep going. We get minus 7 times the integral of dx over, let's see, x plus 1 squared plus 1. It's up to you if you want or need a u substitution at this point. If you did do a u substitution, what would you let u equal? X plus 1. Then eventually you would find du equals dx. Let's see if we just can't integrate this one without going through all this mess of a u substitution. Kind of manipulate this one in our head. For this next line, let me go back here and write that u is x squared plus 2x plus 2 minus 7 times 1 over 1 squared tangent inverse of x plus 1 over 1. And now we'll throw in the 1 constant for the whole thing. You don't necessarily need to write all this extra stuff here. Let's just clean it up as ln of x squared plus 2x plus 2 minus 7 tangent inverse of x plus 1 plus your constant. Okay. Technically, you probably don't need the absolute values here because that parabola is always going to be positive, but it doesn't hurt to leave it there. It's just showing you how to integrate this one. These types of problems come up in differential equations and other applications. So, yeah, it's just what you're going to get a lot in the first chapter or two is a lot of integration techniques. So, in Calc 1, the big trick at the end of the semester was the u substitution. And that generalized the things for which we can find an antiderivative. There's a lot more tricks we're going to learn. We're going to learn some more substitutions with trigonometric functions. We're going to learn integration by parts is a big one, partial fraction decomposition. So there's a lot more tricks to integrating.
But is that going to build on like Calc 4? Are we going to use these tricks?
Yes. Yeah. You're going to see, it's tough to say exactly where you're going to see all of them, but yeah, you do use all your integration techniques. Even in this course, it'll build on itself. When we start doing power series and Taylor series, you're going to use some integration techniques there. So, yeah, it's not the last time you're going to see it. Now, I am a little bit divided, about, how much of this stuff do we need to learn and have memorized, etc. But right now, I'm kind of following departmental guidelines. I teach the stuff that's required so that it meets the course catalog description. And then if you transfer to U of M or wherever, that they look at that and say, okay, yeah, they had this stuff. Okay, great. You're qualified to take this class or whatever, so that you're not going to run up short. Anything else on 36 here? All right. Let's do one or two more. What I'm typically going to do is, go for a while and then give you a break. I like to take 2 breaks during the course. I find that it's tough to stay really, really focused for an extended period of time. So we'll definitely be taking a couple breaks. Let's do some other ones. We're going to stick with the completing the square theme a little bit and take a look at problem number 38. So the integral of 2 over the square root of negative x squared plus 4x dx. Does this one look like it's going to be an arctan? Yes or no? Arctan, what do you think? No, why not? What big impediment to the arctan are you going to run into? The square root. All right, so we might start shaping this into something else, like an arc sine. Now, to shape this into an arc sine, we've got to have it in the form of a squared minus u squared. So that's going to mean some more work with completing the square here. The tricky part for us here is that we've got a minus x squared. So we're going to have to be a little bit careful in completing the square. So I've got a minus x squared plus 4x. And then let's put 2dx up top. You know, I think what I should do first is factor out that negative before I complete the square. When you complete the square, you really want to have a coefficient of 1 in front of your x squared term. So this step is really kind of a waste because I needed to factor out the negative 1 here. My bad. 2dx square root of negative x squared minus 4x. Let's work inside the parentheses first. If you complete the square inside the parenthesis, what number are you going to use? Inside the parenthesis, we won't worry about the negative yet. What number goes in here? Positive 4. Now, putting a positive 4 in there, I've really added negative 4 to this denominator, right? Negative times positive 4 gives me negative 4. So effectively, I've subtracted 4. If I want to keep that in balance, what do I got to do? Add 4. So over here, I'll put a plus 4. And now I can clean this denominator up a little bit. But let's just take a look at that one more time. Because this negative would distribute itself, I get my negative x squared plus 4x minus 4. I don't have a minus 4 here. So to keep that minus 4 in balance, adding negative 4, add positive 4. So you're adding its opposite. Okay. 2dx. This is now a perfect square, so I can write that as 4 minus x minus 2 quantity squared. If you square this out and distributed the negative, eventually you should cancel into that if you wanted to double check yourself, if you wanted to double check me. This is what we wanted. You could, as with the last one, make a u substitution if you wanted to. What would u equal for our u substitution? X minus 2. Well, once again, du equals dx. You know what? I'm not going to formally do that u substitution. Maybe I don't know, a couple of you are looking at like, you know what? Do the u substitution. So here, let's do the u substitution. Du equals dx. So it's going to be 2 du. 4 is not affected by this. It's going to be 4 minus u squared. Which one of these rules can we use? The ones in the book or the ones on the right-hand side board? Arc sine. So that 2, maybe I should have factored it out in front. 2 times the arc sine of u over what? Yeah, that's 2 squared. So 2 there. Last but not least, let's not forget that u is taking the place of x minus 2. So 2 times the arc sine of x minus 2 over 2 plus your constant. And you can write arc sine or sine negative 1. Doesn't matter to me. Okay. How's that one look? Is that one all right? Let's follow that up with another one pretty much like it. That'd be problem number 2. A little bit different, but mostly the same. The integral of dx over the square root of 1 minus 4x squared. In looking at this, hopefully you look at that and say, yeah, that's looking like the arc sine. So you might start trying to manipulate this into the arc sine. Any suggestions on rewriting the denominator? Yeah, so we're going to rewrite that as 2x quantity squared. And then you can make a u substitution from there. So u equals 2x. Now, I think I advertised earlier that when I do these recordings, it's kind of a low-tech installation of the software. From my understanding from the IT department, they said it would cost $800 for them to configure it for us properly. So the upshot is I don't have a pause button. I can either stop it or let it run. So what I do when I run into a place where I want to walk around and give you a chance to work on it yourself is I do a manual pause right here. So there you go. When you see this in your video at home, just hit the fast forward button until it disappears. So that's our manual pause. Let me walk around. I'm going to start learning some names here. So help me out. Tell me your first name or your nickname, however you'd like to be addressed in this class. And I'll start trying to learn those as fast as I can. So, and work on that one. Try and finish it up. pass in a little while to finish learning some names here. Okay, so the rest of this looks like this. du equals 2. Actually, it should be du over dx equals 2. When you multiply both sides by dx, you get du equals 2 dx. Now, my habit is solving for what I have in the integral. And in the integral, I've got a dx. So if I divide both sides by 2 or multiply by 1/2, 1/2 du equals dx. From there, I can make my substitution. 1/2 du over the square root of 1 minus u squared. You don't need to show everything. I do need to see some of your work. I get a little bit nervous about phantom answers, but as long as you show me some of it, that's good. 1/2 inverse sine of u over 1, or just u plus a constant. And u was 2x. Okay. How are we looking on problem number 2 there? Thumbs up? Cool. Let's see, which ones do I want to finish up with? All right. Let's do one with graphing calculator, just to ease us into a break. Problem number 32. We can double check ourselves on our graphing calculator. So let me see if I got this one up and running. Let's see. 4. Graph. Okay, so one of the things that I find a little bit strange is I don't really see them discussing the arc cosine much in this section, but this problem does involve it. So let me help you out with problem 32. One over the square root of 2, 0. Arc cosine of x over the square root of 1 minus x squared dx. Now, at least the bottom looks a little bit comforting, but it's not perfectly what we expect. What's strange is that, like I said, in the section I don't see much reference to the arc cosine. So that's why I'm going to do this one for you. And a lot of our goal here is to practice some numerical integration on our calculators. The trick here is to let u equal the arc cosine of x. Now the derivative then, derivative of the arc cosine is going to look a lot like the derivative of the arc sine. It's going to be a 1 over the square root of 1 minus x squared. The only difference is that there's going to be a negative. So it's going to be that negative here. All right. We can also change our limits of integration. I like doing this. You don't have to do it. Some do, some don't. It's up to you. But let's just get rid of the old limits and work with the new limits. So u of 0 is the arc cosine of 0. What is that? It's really asking you what angle has a cosine of 0. Now remember, cosine is your x-coordinate on the unit circle. That x-coordinate is going to be 0 at pi over 2, at 90 degrees. So arc cosine here is going to be pi over 2. Arc cosine of 1 over root 2 Now, if you don't remember these things, and it's certainly understandable and very easy to forget these things, here's what you can do. Put your calculator, first of all, in degree mode, because you're not going to recognize these decimals if you get pi over 6 or pi over 4 or pi over 3. They're just going to be numbers. So let's put our calculator in degree mode. Now, calculus is done in radians, but for this part, we're just going to backtrack into degrees. We want the arc cosine. So another way to think of that is the cosine inverse of 1 over root 2. So second, and then cosine. 1 divided by the square root of 2. On the new calculators, you have to hit the right parenthesis or the right arrow to get out from underneath that radical. And there you go, 45 degrees. Don't put 45 as your limits of integration though, right? What's 45 degrees in radians? Pi over 4. So there we go, pi over 4. Is that a helpful trick, to help remember and figure out what some of these things are? I don't imagine everyone has their unit circle memorized, at least not this early in the semester. So thumbs up, thumbs down, feedback. Okay, a couple of you. All right, thank you. Let's see here. All right, so that's good news. We've got that negative here. We probably should solve for that. So minus du equals 1 over the square root of 1 minus x squared dx. That's exactly what I have here between these two terms. That's my u, and here's my du. And I've got my new limits of integration. So it's going to be the integral from, let's see, 0 is going to be pi over 2 to pi over 4 of u times negative du. Okay. You can factor the negative out in front. And this one is just a friendly old polynomial. Hopefully no problem in integrating u. What's the integral of u? Yeah, a couple ways to say it. U squared over 2, 1/2 u squared between pi over 2 and pi over 4. Depending on how thorough you want to be and how careful you should want to be, you can graph these things. So here's our function graphed in Desmos. If you want to make your graph a little darker, just go to projector mode. That helps out a little bit. But we only want this on the interval from 0 to 1 over root 2, so there's kind of a restricted version of this graph. When I integrate this, am I going to expect something positive or negative when I integrate this? Negative? Let's see. Let's make that less than or equal to here. And then I want to restrict this for y is greater than 0. All right, so essentially what this integral is giving me is this area right here. Since that area lies completely above the x-axis, I expect something positive. And all I'm asking you to do is, when you're working on these things, think critically. Whoops, wrong one. Think critically about your answers. If you're getting a negative answer and you expect a positive answer, there's something wrong. So minus 1/2 times u squared, pi over 2 to pi over 4, pi over 2 squared minus pi over 4 squared. One half times pi squared over 4 minus 1/2, or excuse me, minus pi squared over 16. And let's see, I lost a negative here along the line. Let me show you a little bit of a trick to avoid some of the nasty work with all the fractions. It's not that bad. I hope you can do it. If you factor out the pi squared, you're left with 1/4 minus 1/16. Now, I'm not going to put in the pi squared into my calculator, but I am going to do this. Let's take 1/2, which I'll write as 0.5, or you can write negative 1/2. Negative 0.5 times, parentheses, what's 1/4 as a decimal? 0.25 minus, and 1/16 I'm not going to show off, but there you go, minus 1/16. Something's wrong. Should end up with something positive here. No. Oh, you know what? I think I got these in the wrong order. Yeah. When I substituted these in, this should be the other way. It should be the 4th here and the 1/16 here. Okay. But the nice thing, though, and have you seen this trick before? Let's put it in the right order. Negative 0.5, 1 divided by 16 minus 0.25 is that your calculator convert these things to fractions. You hit the math key, answer the fraction, and there you go. 3/32. So flip these, but you should end up with 3/32 times pi squared as your final answer. You can check these things. You can check them on your graphing calculator by doing a numerical integration and comparing it to this answer. So we'll do that, and then we'll take a quick break. If you go to the math button, the 9th option down is for an integral. Okay, that's pretty nice. So we're going to integrate from 0 to 1 divided by the square root of 2. If yours doesn't look like this, you can update your operating system so that it will, as long as you have a TI-84 or later. And then the arc cosine, inverse cosine of x, divided by the square root of 1 minus x squared. And of course the variable integration. You should be able to compare that to the numerical answer here. Did I type that in right? It doesn't look... No, this one won't be a fraction. No, it won't be a fraction. That doesn't look... Let's see, pi squared 27. No, those don't look right. They don't look like they match. Let's see. So 3 pi squared divided by 32. No, they're not matching. All right. So what's wrong here? Did you get... Oh, that's it. Yeah. Whew. Thank you. So mode, radian, yeah, that'll make a big difference. There we go. All right, good. Let's take a break here, and I'll see you in 10 minutes. We'll finish up section 5.8.